contestants are present. And that is the problem with the existing data sets also, because somewhere in the background, it is leveraging the bias, irrespective of the fact that whatever the model you are building, whatever the internal layers you are considering, whatever the weights you are going to adjust, but ultimately the data that you are going to use, it is biased against certain group of people, or it is biased against certain data which should be considered. One more example, if I say, so you can refer to this website and you can see a lot of other faces also. The name is "This Person Does Not Exist." So this person does not exist.com, and Karas et al. Have worked on the synthetic images which are available. So actually, these are the faces of the people who actually do not exist. And based on the facial features of various people like Asian, European, US, and distributed across the world, they have created these synthetic faces. So actually, these are synthetic faces, and a lot of synthetic faces are available over this website. And people are using these faces, these synthetic images data set, for their own purpose. But think of a situation, you are using this data set to classify the people, to identify the face of the person, and actually these are the person who do not exist. So what will be the consequences of that model? That is something that we should consider and we should rethink about them. One more, bias based on racial. So this is more dangerous because they are implicit and definitely they are prevalent. So this is something, if you look at the top row here, so it has the players who are from the dark skin background, and the model is predicting all the players as playing the game of basketball, irrespective of whatever the uniform, whatever the sports jersey they are wearing, irrespective of whatever the sport they are playing, whatever the action they are doing, but it is predicting all the people as playing basketball. And in the bottom row, if I see, so for the same people, like if they are doing the same action, if they are doing almost the same sports jersey, but the model is predicting them ping pong ball, rugby, baseball. And what is the reason behind this? Let me tell you. So if the person has features up to certain features like a mountain man, a mountain based individual, so it is predicting, let us say if it's a Chinese or it's a Singaporean person. So ultimately the model is biased towards predicting it to be a ping pong ball. Although you can compare these images, the action is almost same, the uniform is almost same. And even in the last case, so if you apply to identify the action, or if you apply to identify the action in the bottom image, so action is same, but for the bottom image, the model is predicting it to be a ping pong ball. And for the top image, the model is predicting it to be a basketball. Almost the same cases here, the same jersey, the same players from the same team, but because the person in the top is from a dark skin background, the model is predicting it to be basketball. And because the person in the down is from a fair skin background, the model is predicting it to be a rugby ball. So that is something which is really problematic. And this is very dangerous because it is based on the racial bias. So being a machine learning expert, being a machine learning researcher, if you are looking to develop any machine learning algorithm or model which considers the players from different geographic locations, from different communities, from different groups, so please be careful about this because this can be dangerous. Now, let's talk about bias, because we have seen if the bias part is not handled properly, so how it is going to affect the world. So let us talk about some types of bias. I'm not going to discuss all types of bias. There are more than 25 types of bias available. So I'm just going to discuss a few of them to get an understanding of the categorization of the bias and how we can handle it. So the first type, that is historical bias, it considers the socio-technical issues in the world, and it can seep from the data generation process, even if your model is working perfectly fine. For example, in 2018, image search result for women CEOs. So it ultimately result very fewer female CEO images. And the reason being is that only 5% of Fortune 500 CEOs were women. So this is something, this is a fact which is related to socio-technical issues, which is already available from the Fortune 500 data which is available. And it would cause the search results to be biased towards male CEOs. So that is something, the model bias, the model is giving some biased results due to the socio-technical issues, and it falls in the category of historical bias. The second type of bias, that is representation bias. So it happens from the way we define and sample from a population. So given a population data, now how we are going to define it and how we are going to sample it is going to affect the performance of your decision. Lacking geographical diversity in data sets like ImageNet, one example we have seen. So how this data set is being organized because of the lacking geographical diversity. So it is an example of this type of bias, and definitely demonstrates a bias towards Western countries. The third one is measurement bias. This happens from the way we choose, utilize, and measure a particular feature. Okay, so it is up to us how we are going to utilize a particular feature based on the measurements and how it is going to affect. For example, bias was observed in Compass. We discussed about this tool, which is used in the session courts of the US. So how it affected the overall decision of the jury members, the decision of the judges based on the prior arrest and friend family arrest due to the African Americans present, and due to this, the level of riskiness or crime was increased. So based on these measurement parameters, it affected the performance of the model and it was biased against the African Americans. The population bias, it arises when statistics, demographics, representatives, and user characteristics are different. So ultimately now in a given population, there are various differences based on the demographics, representatives, and their own characteristics. And ultimately it leads to population bias. For example, different user demographics on different social platforms, such as women being more likely to use Pinterest, Facebook, Instagram, while men being more active in online forums like Reddit or Twitter. So based on this population, the characteristics of the population, there will be a bias in your data that we need to understand. Aggregation, so when false conclusions are drawn from a subgroup based on observing other different subgroups. So the example that we discussed for medical, now let us say if there is a machine learning model which is being made for the diabetic patients. So we know that the diabetic patients have differences across ethnicities and genders, and more specifically the HbA1c level that are widely used in diagnosis and monitoring of the diabetes. So these factors, the ethnicities, the geographic locations, the demographic, the gender, because these factors and they have different meanings and importance across the different subgroups and populations. In India, we used to eat sweet more. Just this is a trend and culture in our country. So we cannot consider a specific model which can consider this part and which can predict whether the HbA1 level for a European is as of the Indian. So we cannot think of developing a single model to perform the tasks which are distributed across the globe in terms of ethnicities, genders, and their properties. And we should consider different submodels and we should aggregate them. So this is something which falls in the category of aggregation bias. Now, types of bias towards model security. So these are three bias that I'm going to discuss here, and they are more related towards the model security. What these bias are, the first one is evaluation bias. It happens during model evaluation. For example, use of inappropriate benchmarks for evaluation of applications. So whatever the benchmarks we are going to use in the model, it is dependent, because if you are going to change this part in your model, ultimately it will start creating a bias towards the evaluation. So this is a bias, but it is intended, it is diverted more towards the model security. The second one is omitted variable bias. So omitted variable bias occurs when one or more important variables are left out of the model. For example, the tool of compass, again, if we discussed, so because it is biased, because there are certain important variables that are left out of the model, and due to which the model predicted, the model gave some biased results against a certain community. The third one is funding bias. And again, the Cambridge Analytica scam for election campaign of Donald Trump. The funding bias arises when biased results are reported in order to support or satisfy the funding agency or financial supporter of the research study. So in 2018, the Facebook itself accepted this problem and the data was misused. And this should be taken into consideration. The output, the result of the model should not be biased towards a particular agency or any financial supporter or the research study. So this is just a broad diagram which shows, because there are various types of bias, and I have discussed a few of them also only. So it's a diagram which shows the different types of bias which are available at different instances in a user interaction with data and data interaction with algorithm. So in this cycle, and in which particular phases, which type of biases should be present, this diagram shows a representation of that. Now, we have seen how the bias is going to affect the functioning, the decision of the model, and why it is important. A few types of the bias we have already seen. So if we want to target the bias, because it's an emerging field, and from this dark side aspect, how we can target, some broad level techniques are available. One is about pre-processing. So these techniques try to transform the data so that the underlying discrimination is removed. So if the algorithm is allowed to modify the training data, then pre-processing can be used. As of now, whatever the pre-processing we used to do the pre-processing for better functioning of the model in order to give a good decision. But irrelevant of the fact that there may be bias present. And if we need to consider this part, this factor should be considered with respect to the bias. And if the algorithm is allowed to modify the training data, so pre-processing should be done for targeting the bias, the type of bias which is present. The second technique is about in-processing. So these techniques try to modify and change state-of-the-art learning algorithms in order to remove discrimination during the model training process. So if you say already you have a data and you are well aware about the fact that your model is giving some output, some result which is biased against a group of data, a group of community or something. So if it is allowed, so change the learning procedure for a machine learning model. So you can just use it during the training phase, either by incorporating changes into the objective function or imposing a constraint during training. So being a machine learning researcher, being a machine learning engineer, it is up to you. It is your responsibility to take care of these parts if you are well aware about the types of bias which are available in your data. Apart from this, we have post-processing, and definitely as the name suggests, so it is performed after training by accessing a holdout set, which was not involved during the training of the model. So if the algorithm can only treat the learned model as a black box without any ability to modify the training data, then post-processing can be used. In this case, we can just consider the model as a black box, and then we can apply the post-processing in which the labels assigned by the black box model initially get reassigned based on the function during the post-processing phase. So after getting an output, we need to reassign the labels and we need to treat the model as a black box if this is the situation. So these are some of the ways by which you can target the bias. But apart from this, there is one more problem, that is algorithmic fairness. And bias is something which is related to the data, which is ultimately affecting the functioning of the model. But let us say if the data is given in a good form, but how your algorithm is going to behave, the fairness of the algorithm also plays an important role. And if I go with Mehrabi et al., so algorithmic fairness, they have classified into three parts. That is individual fairness, which gives similar predictions to similar individuals. The second one is group fairness, which treat different groups equally. And the third one is subgroup, which is like a combination of the previous one. So it intends to obtain the best properties of the group and individual notions of fairness. It is different than these notions, but uses both of them to obtain a better outcome. So whenever you are targeting the algorithmic fairness, these are the three parts of the fairness that you can consider. And let me show you how we can impose this fairness for better functioning. So let us say we have a situation where we have a data regulator, a data producer, and a data user. So let us say data user is nothing but your machine learning model. That's it. Coming to data producer, so it is the representation of the data in a more fair form so that the available bias, underlying bias can be removed. And in order to generate this kind of bias, to generate this kind of fair data, to represent the data in a better way, we need to take output from the data regulator. So what is a data regulator? It is a specialized entity that we can consider in our system. And based on certain fairness criteria for the underlying data, it can give instructions to the data producer that this is certain fairness criteria, and based on this certain fairness criteria, the data should be produced. Specifically, if I talk about, so it identifies the sensitive attributes in the data, and based on the sensitive attributes, it creates a fairness criteria based on the distance, whatever the distance it is going to compute. And when training, so it interacts with the users, experts, judges, or policy to determine the fairness criteria. And once the fairness criteria is established, it can give instructions to the next entity that this is certain fairness criteria, and whatever the data you are going to represent, it should be in the form of this fairness criteria. It should satisfy this particular fairness criteria. Maybe for this purpose, although it's optional, it can perform auditing also. So given the input data and output data, it can simply check, are fairness criteria satisfied? This is the job of the data regulator for imposing fairness for better functioning of the model. Coming to the other entity, the data producer, which takes input from the data regulator. So it computes the representation given the fairness criteria and input data. So given the inputs and fairness criteria, the output is a learned representation. So ultimately the given data is mapped to, let us say, some sanitized data. It is more clean data, which is transformed, which is processed, which is represented as per the fairness criteria given from the previous entity. And now this data is going to be given to the data user, which is nothing but a machine learning model. And given the sanitized data as input, the job of the machine learning model is to simply give the model output as per the given data. So it computes the machine learning model given the sanitized representation, and it only need to remain compliant with the pre-specified expectations, and it should avoid adding new features that can result in fairness violations, because it is the data regulator and data producer who have already worked on the data for its better representation. And once the data is well sanitized, the data is represented in a good way, it is given to the machine learning model. So it should avoid any new features that can be added, and ultimately it is going to violate the fairness criteria. So this is how, through these three entities, we can impose fairness for better functioning of the model. Now, if I revisit the dominating problems, so for the dark sides of machine learning, we have learned about leveraging bias, what are the problems, what are the real-time problems that are now gradually coming, and what are the algorithmic fairness problems and how we can impose the fairness criteria for them. These points we have covered. In the next part, I'll be covering about model security and data privacy, which is always a problem. But for a machine learning algorithm, for a machine learning model, why these are important to consider, let us see. So because we are living in a smart world and everywhere we are related with the machine learning models. Ultimately, if I talk about your smartphone, so every app, almost every app that you are using is directly or indirectly connected to certain remote servers, that is cloud. And you are sending your data, you are receiving the result, whatever it is reflecting, that is a normal process. And we know that as part of the data security, whatever the data you are sending is in the encrypted form, whatever the result you are getting is in the encrypted form. Ultimately, this communication is end-to-end encrypted. So whatever the cloud or remote server you are accessing, ultimately your data is being transmitted in secured form, you are getting the result in secured form. That is fine. But there is an important question, how we can process the data at remote machine learning models, which are located at some third-party cloud servers without decryption, because it is important to note. Let us say from the gallery of your mobile phone, you are sharing the images through certain app. Let us say you are interested to apply certain filters, or you are sending your images for some kind of functioning, let us say image dehazing or any other filtering to some remote machine learning model. So your images are ultimately being transferred to this remote machine learning model, which is stored at some cloud service provider. So for decryption, whatever the encrypted image you are sending, it has to be decrypted. And once it is decrypted, it is processed for better appearance, whether it is for nighttime haze removal, denoising, whatever the functioning you want. And after that, it is encrypted again. And this encrypted result is being transmitted to you. So the communication is end-to-end encrypted. But if I talk about this remote server, which is the cloud infrastructure itself, it can see all the data and it can misuse your data. And this is actually happening. If you are searching for a particular medicine for, let us say, 2 or 3 days continuously, so maybe after some time you will start getting emails or you will start getting messages regarding the medical expert available in your area for that particular disease. Or if you are continuously using some features which are related to image processing, so after some time when you open your any social media account, you will start recommendations for using that service automatically independent of whatever the device you are using. So these are certain problems because these are certain details which are related to the personal life of the people. And inside end-to-end encryption, the data is being decrypted at the remote machine learning models. And we need to think about techniques, the methods in which we can send the data in encrypted form, we can receive the data in encrypted form, and the most important thing, we can process the data in encrypted form. So ultimately, no decryption is required at all. And when we are talking in terms of encryption, so definitely there are computational and storage overheads which are related to this. So there is a paradigm that we call privacy preserving computing, and it involves processing the data in encrypted form. So just a pictorial representation, it's an example where a plain image is considered, and let us say we want to colorize this image over some remote machine learning model. So this image I am going to encrypt, and this encrypted image I am going to give to the remote machine learning model. This model itself can perform the processing over this encrypted image only. No decryption is required. And after this, when I'm going to receive this encrypted image and when I decrypt it, I can see the effects of processing. So this is privacy preserving computing, where we are processing the data in the encrypted form and no intermediate decryption is considered in this overall situation. So this encrypted domain processing or privacy preserving computing, it finds place in all the scenarios where privacy is the primary concern. So it is achieved using homomorphic encryption. This is one way. The second way is obfuscation that I will be discussing after 10 minutes. So what is homomorphic encryption? It is an advanced form of encryption, we can say, and ultimately it allows us to process the data in this encrypted form. So it gives the equivalent effects as in unencrypted or plain form. For example, if I have my plain data in the form of A and B. So if I encrypt A, I'm going to get A cap. And if I'm going to encrypt B, I'm going to get B cap. So A cap and B cap, they represent the encryptions of A and B. And what this, for example, additive homomorphism property says, if I am going to perform an operation between the encrypted values of A and B, and if I am going to decrypt this encrypted values of A and B, ultimately I am going to get a result, which is an addition of the plain values, that is A and B. This is what homomorphic encryption says. And the good part here is that the encrypted values, that is A cap and B cap, they do not reveal any information about actual secret values, that is A and B. So if I go to the classification of homomorphic encryption, because it depends on the user, which level of security you are interested and which particular operations you are interested to perform. There are various computational and storage overheads associated with homomorphic encryption. And broadly, it is classified in 3 categories, that is fully homomorphic encryption, partially homomorphic encryption, and somewhat homomorphic encryption. So I'm not going into its very detail, but let me broadly tell you, if you want to perform any number of operations over the encrypted data, so it falls in the category of fully homomorphic encryption. If I say that you are given an encrypted data and you can perform only one or a specific kind of operation only, it is limited to a certain operation, that is something which is related to partially homomorphic encryption. And you can perform certain operations, either one kind of operation, one category of operation, or other category of operation, but there is a limit. Up to that you can perform, but after that you cannot perform. The threshold is going to be reached. So noise level will grow, that will cause your data to be ineligible for decryption. So this is the 3rd category, which falls in somewhat homomorphic encryption. So these are the types of homomorphic encryption, and based on the operations that you need to perform, you can choose the available systems which are available. Now, I'll just discuss one homomorphic encryption scheme here, just to get how we can process the data and why it is important. Like if I say I have a value 100, so after encryption, it will be converted to some encoded form. So this encoded form I can send to my model, and over this model, I can process it in the encrypted form only without performing any decryption. So the normal process that you are doing in a machine learning way, you can perform the same process using homomorphic encryption in a complete secured form. So it's a well-known technique that we call, that is Shamir's secret sharing. And what this technique does, given a prime number, a secret A0, the secret sharing polynomial to generate the shares is as follows. So A is the secret value. Let us say I have 100 as the secret value. So I need to put this as A0, the first coefficient, and the next coefficients from A1 to AK-1, they are random numbers. They are randomly chosen from 0 to P-1, where P is a prime number. K is the number of shares that we are interested to get. So this is Shamir's polynomial. And we can just select n distinct integer numbers to put in place of x. And based on this, we can generate multiple shares in the range of 0 to P-1. And if I consider one pair, so here I need to represent it using its share number and share value. So I can generate, if given 100, I want to generate 5 different shares, I can generate using this Shamir secret sharing polynomial by putting these AI as the random numbers and putting separate values for x, and I can get these values from this particular polynomial that I can distribute to different cloud servers, and I can perform the processing in the encrypted form. For decryption or reconstruction, I can say this is Lagrange interpolation, which is used, and we need to put here the x as 0, and we need to compute the inverse modulo with prime in order to get the value reconstructed after processing. So I can directly come to an example to demonstrate you how it works. So let us say I have my secret value A as 100, and I have the prime P as 151. So if I take the first coefficient as 19, so polynomial equation for K as 2 is defined as, this is a simple polynomial equation for this case, A0 plus A1x mod of P, and in place of A0, simply I'm going to put 100. In place of A1, I'm simply going to put 19, and P, we know that it is 151, and one by one, we need to consider the values of X here. So this is in a more normal form, 100 plus 19X mod of 151, and given the values of X1, X2, X3, and X4 as 1, 2, 3, 4, if I put here 1, then 2, then 3, and then 4, I'll get these resulting values, that is 119, 138, 6, and 25. And just let me quickly club these values. So share number 1 with its value 119, share number 2 with its value 138, 3 with 6, and 4 with 25. These are the 4 shares that are being generated from this Shamir secret sharing polynomial given these secret value and coefficient values. So for reconstruction, I just simply need to put it in the Lagrange interpolation form. And in this Lagrange interpolation form, I just need to put this X as 0. So when I'm going to put this X as 0 and further solve it to get the inverse modulo under 151, I'll get the value 100 back, which is the secret value. Now, the important point to note here is that we started with 100, we are getting 100 back. And if I take these shares, so my first share is 1,119. If I simply add 10 here, so it will become 1,129, and second 4,35. I'm going to add 10 to this 25. So 1,129, 4,35, the 2 shares if I take here, and in place of 25, if I put 35, in place of 119, if I put 129, rest of the things will be same. So ultimately it will give me the reconstructed value as 110. This is the effect of processing. These are the 2 shares after processing, and when I reconstruct it back, I get the modified value. This is what we call additive homomorphism. So this is about additive homomorphism, and this property you can utilize in your machine learning models. How you are going to utilize it? Let us say you have the client data or any client company data. You can encrypt this data simply using homomorphic encryption, and you can send this encrypted data to any machine learning model which is located at some remote cloud service provider. So at the machine learning model, in order to compute the coefficients, wherever the additive or multiplicative operations are to be performed, you can simply perform these operations over the encrypted data. As an example, we have seen in the previous 2-3 slides. And once the data is computed, this encrypted result you can give back to homomorphic decryption or reconstruction, and this you can give back to your client. So ultimately your client is giving a data in a complete encrypted form. In the meantime, the data is not going to be decrypted anywhere, and ultimately after the processing, the data is getting back to the client company. This is how you can secure your model parameters using homomorphic encryption. But there are certain problems. What these problems are, ultimately, if I say, so they are related to the computational and storage overheads. So there are certain schemes which are available in your screen. And if I consider the Shamir secret sharing, so it expands the data size by n times, because given the data, we need to generate its multiple shares. So ultimately the size is expanded by n number of times. We need to consider 5 different cloud servers. Although the security of the model is guaranteed, but more number of resources we need. Coming to some other well-known techniques, let us say naive failures scheme. So the data size is expanded by 170 times, or in its optimized way, it is expanded to 85 times, which is still a large number. That is a problem with homomorphic encryption. But because this is the beginning, it is a new field, research communities are using homomorphic encryption, and they are using this well-defined techniques to secure their model parameters to perform the computation in an encrypted form without performing any decryption. So this is one aspect of securing your model, securing your data using homomorphic encryption. And the other aspect is about obfuscation. What this obfuscation is about, I'll come to this explanation with the example of a human action recognition situation. So let us say you are the owner of a particular surveillance site, and using computer vision techniques, you want to get to know about the suspicious human actions which are being performed on your surveillance site, whatever the factory premises or whatever the premises you are owner of. And independently using the cloud-based services in any remote device, you can just see if there is any suspicious human action which is being performed on the surveillance site. So ultimately, this data which is being generated from these video cameras, you can simply encrypt this data, give it to the trained machine learning model, which is located at the cloud server, and you can get the recognition result in your remote device. But we need to consider the obfuscation part here, because we are not going to talk about homomorphic encryption, but some other techniques. So there is one thing which is related to identity preservation. What this identity preservation is about, previous visual privacy methods, if we say, so they include mosaicing, blurring, scrambling, or encryption. They are direct methods which can transform the data to some other domain, and data becomes very tough to understand. And one of the example for weak encryption was used by YouTube for face blurring. It was introduced by YouTube in 2012, where it simply blurred the user faces, or mosaicing was performed over the user faces, just to preserve their identity, the name of the person, the face of the person, any identity of the person should not be revealed. But problem is that even after this blurring, we can say that a lot of background information is visible. Even the clothes of the users are visible, due to which their identity is still getting revealed and people are able to recognize them. So that was a problem, and YouTube itself stopped this concept after some time. So in order to overcome these kinds of problems, a few research works, they have proposed to utilize extremely low resolution images, for example, 16 by 12 kind of images. So given a very large image, you can extremely resize it so that it becomes very hard to achieve, to identify any person who is available in this particular image. But there are certain drawbacks for simple image obfuscation also. What these drawbacks are: data subjects privacy loss. The low resolution images, for example, if you can see, so these are original images, these are low resolution images, they are directly generated. And due to this, they are vulnerable to statistical and differential attacks. Even in one of the research papers entitled Defeating Image Obfuscation with Deep Learning, so author claimed higher re-identification accuracies for these simple techniques, simple obfuscation techniques, against 4 standard data sets, including MNIST, CFAR10, AT&T, and Face Scrub. Also, there is one paper named Pulse, which is a framework for efficient photo upsampling. So it's a model itself which is upsampling the given mosaic images. So you can see if this is the given image, from this given image, how it can upsample this image, it can reconstruct the image based on the features which are available. So we cannot say like we can simply resize the images and we are securing the data, we are securing the identity of the person, that's it. This is not the case. We need to think of some robust techniques where if you are going for obfuscation, you are not using homomorphic encryption, but you are going to adapt some obfuscation technique. So it should better take care of whatever the privacy parts, whatever the privacy concerns which are available in the underlying user image. So if I compare it simply, so this is my original image, this is the full mosaic image, this is face blurring, this is image scrambling, and this is image encryption. And we know that based on these statistical and differential parameters of security, image security, if I move from left to right, so the correlation between adjacent pixels was really high in the plain image, which is drastically reduced in an encrypted image. Similarly, if I compute the randomness property by computing the entropy parameter, so entropy is less in the original image and it is gradually increasing as we are moving towards the more encrypted image. And differential percentage is the difference between two encrypted images. For these images, it is 0 because it's already getting generated in the similar way using interpolation, whether bilinear or bicubic. But if I talk about image scrambling or image encryption, yes, the difference percentage significantly higher. So what I'm trying to convey from this figure, if we move from left to right, we can see that the security of the image is getting improved. But this is an opposite case with the model, because the model needs data in clean form. And if I give this kind of data, the model cannot work. So it's a trade-off, like whether you want your model to work on higher accuracy or you want your model to work with high security parameters. So to overcome this problem, to establish a relation between the security and recognition accuracy of the model, we have worked on a position-based superpixel transformation where we divided the image into equal number of blocks. And for each block, the entire value of the pixels that we are going to superimpose in the form of a single pixel, we are going to randomize it. Ultimately, this is a super pixel that we are going to generate. But this super pixel, we are not going to generate based on the color features of the image, based on the pixel intensity values or structural properties or luminance or radiance present in the image. But we are creating this super pixel based on the position of the pixels itself. So for each image block, the underlying pixels are considered, their superpixel is generated, and that superpixel is being randomized with a noise, and we are bounding that noise with a particular prime also for an adversary to not to get back, to not to revert back to it. So it's like a one-time pad that we are adding to each block value, and this encryption is something which is non-invertible. So you cannot perform decryption, you can only go in one direction, and this image we are going to use in the machine learning models. So this is a pictorial representation given a particular image. You can divide the image into number of blocks, and for each block, we are going to add a particular noise like a one-time pad, and it's an non-invertible encryption. So it's a single way encryption, and this is the obfuscated low resolution image that we are going to get. So in every image, it is robust against the differential and statistical attacks, because in every block and in every image, every time, the random noise that we are going to add is completely different. And that is the reason if we try to take out the difference between two encrypted images, it will be a new encrypted image, but not a darker image, which is the problem with the mosaicing and blurring techniques that we have seen in the previous slides. So when we use this and when we analyze this, so you can see that image information is more obfuscated with higher block sizes. So if I say my block size is small, definitely the size of the image is going to be big. But if the blocks are getting higher, the image size is going to be small. So this is just a visual analysis of how the block size is going to affect the image. So this is my block size for P was 2, and this is my image size. This is the visual description for the same, and we can see, like, as we are increasing block size, we are going from left to right. So we are going from left to right. After this, we are again coming to this. So when we are going from left to right, we are increasing the block size, and as we are increasing the block size, more number of pixels are getting accumulated in a particular block that we are getting transformed into the form of a super pixel, and we are adding sufficient noise to it in order to get a good obfuscated image. So for the final block size, if I say this is the most obfuscated image, where block size is 32 cross 32 and image size is 7 by 7, because a standard image size of 224 by 224 we considered for this purpose. So when we are moving towards higher block size, definitely the details, the data is getting destroyed, is getting compromised, but at the same time, the security is getting increased. So at one point we have security, and at one point we have accuracy. And it is the wish of the user, whether the user interested for more security or the user is interested for more accuracy. This is with respect to obfuscation part. So at the experimentation level, we perform certain experiments over the UTD MHAD data set, which is a human action recognition data set. Total 27 classes are there in the data set. And when we took the motion history image and depth motion maps of the obfuscated version, when we used it for training and testing purpose, and the underlying model was MobileNet that we used at that time as CNN in our framework. So this is a comparison of the recognition accuracies with respect to the block size. And again, I say the same thing when we are going from left to right. So image size is getting reduced, block size is getting increased, and definitely because we are moving towards more security. So ultimately, the accuracy is getting reduced in this fashion. So if we want more accuracy, we need to compromise with the security. If we want more security, we need to compromise somehow with the accuracy. And it's a trade-off analysis between both the entities, but still, as of the state of the art solutions, it's one of the best solutions. Why so? So let me show you this figure here. If I consider the existing image encryption schemes, the visual data schemes. So given the original image, if we go for its full mosaicing part, this is something which is used by some of the research communities by directly taking a high resolution image to its low resolution part and using this data directly in the model, saying that it is preserved, it is preserving the identity of the person. So that full mosaicing is something where a lot of data is available. And that is the reason if I go with full mosaicing, so 88% accuracy is achieved with the model. But if I go for face blurring, where nothing is going to be encrypted, only the face of the person is going to be blurred. The technique which is used by YouTube in 2012. So here more information is available except the face of the coming person, underlying person, and that's why the accuracy is definitely high, 89.19% in this case. But for both the cases, we can see that a lot of visual information is available. And in one of the paper that I discussed, that is Pulse, so upsampling is possible for this image, and the image can be reconstructed back to its original form. It can be reconstructed back to this. So this is not at all secured. Coming to this part, if I say, so only face of the person is blurred. And because only face of the person is blurred, a lot of background information, including the clothes and accessories of the person are available. So from this available information, the person can be identified. And that is a problem. So for the first two techniques, if I say, recognition accuracy wise, they are good. But from security point of view, these methods are weak. They are vulnerable to statistical and differential attacks. And when you are sending your data to a remote machine learning model, we cannot send data in this form. Coming to image encryption techniques, so if I go for scrambling where no information is available, the pixel values are distributed uniformly in a scrambled way. So for image scrambling, the accuracy is 6.90. But coming to image encryption, where complete security is achieved, we can say that the pixel values are properly distributed, permuted, and their values are also modified using some of the diffusion techniques. Coming to full encryption, you can see that how the recognition accuracy is decreased here up to 4.24% only. So there is a big gap between these two techniques and these two techniques. And through the proposed method, we tried to map this gap. This is the proposed method, the image that we are getting from the proposed method. We are trying to preserve some information, but no information which is sensitive to the user. And the accuracy that we are getting is 83.48%. So this is something which is acceptable given the gap between the existing visual data image encryption schemes, which are weak and which are completely robust. The gap is very high. And we tried to map this gap with the proposed method, getting a good ratio, a decent ratio between the privacy and security and recognition accuracy using position-based superpixel transformation. So this research is published in Expert Systems with Applications. If you are interested, you can refer to it. So that's about my today's point. And these are the references that I used. Thank you.
Saishu, shoot us. आओ, आजो बाहर आजो, चलो आओ चले. Let's go. Come. इधर से आओ. बैठ बेटा. Saishu, बैठ बेटा. See? डालो shoot.
Thank you, sir.
Thank you.
Any queries?
Yeah.
Uh, I just want to give vote of thanks, sir. On behalf of RGPV, I extend a really hearty vote of thanks to our expert, Dr. Amitesh Singh Rajput, who spared time from his busiest schedule to grace the occasion. Today, we had an opportunity to hear your thoughts on machine learning. When do we use machine learning? The bright sides of machine learning, like recognition pattern, prediction, recognizing anomalies, machine learning dominating the headlines, the dark sides of machine learning with the real-time examples like dam operations with machine learning, chemical factory operations, and others. Some dominating problems and its solutions, leveraging bias like fairness, problem of squid decision, compass problem, sensitive applications like medical domain, ImageNet and open images data sets, some few important types of bias, biasing towards the model security, targeting biases for better functioning, and privacy preserving computing, homomorphic encryptions, encrypting model parameters, problems with homomorphic encryption, understanding the obfuscation with secure human action recognition, identity preservation, drawbacks of simple image obfuscation, existing visual data encryption, and comparison with existing image encryption schemes. This will surely be going to encourage us in our future events and in research. Thank you very much, sir.
Okay, thank you. Thank you, RJPV. Thank you all the researchers, academicians present here. Thank you, Shikha ma'am, for giving me a chance. I hope that you all enjoyed the session. So thank you.
Thank you, sir. So it's time for a tea break. 12 o'clock, we again meet for the second session of the day.